Today we're going to talk about slope fields. So a slope field is a graphical representation of the set of slopes of a differential equation. Some of our differential equations are equations that have derivatives in them. So we can plug in points on our, we can plug in coordinates in for the x and y in our differential equation, and it will tell us what the slope is equal to. If we put all these slopes, if we find a lot of slopes, a lot of different points, we end up with what's called the slope field. And then from the slope field, we can kind of get a graphical representation of the solution to the differential equation. That's important because sometimes we can't separate variables and integrate. We can still at least get an idea of what the differential equation is just by plotting the slopes of the function. So let me show you what it looks like and it'll make more sense. So this example one says, find the slopes given by the differential equation dy dx equals negative x over y. So this is my differential equation, right? dy dx is the slope, and so if I plug in my x and y coordinate into that negative x over y, I end up with the slope of the function at that point. So for example, at the point 3, 2, dy dx would equal negative 3 over 2. So that means that's my slope, right? So at this point, at the point 3, 2, I know the solution to that differential equation will have a slope of negative 3 halves. I'll plug in negative 1, 3, so I end up with positive 1, positive 3. So negative 1, 3, that's my slope. I'll plug in negative 2, negative 1, so that would end up being a positive 2 over a negative 1. So I have a slope at the point negative 2, negative 1, I have a slope of negative 2. If I plug in 2, negative 2, so I put negative 2 in for, or 2 in for x, so negative 2 and y is negative 2, I end up with a positive 1. So the slope at the point 2, negative 2, the slope of the solution to my differential equation is equal to 1. It's asking, like, why can't we find a slope when y equals 0? Well, if I plug 0 in for y right there, right, the slope's going to be undefined. So at any point where y equals 0, the slope will be undefined. So what we're going to do is we're going to take this slope field off to the right, and we're going to fill in the slope for all the remaining points. So some of them already have the slope drawn. So you see at these points where we've got the little, some of them already have those slopes drawn right across there, but some of them don't. So we're going to fill in the rest of this. And this actually is the same function we were just doing. So I know the slope of the solution to that differential equation is equal to negative x over y. So if I pick, for example, the point 1, 2 right there, if I plug 1 in for x and 2 in for y, I get a negative 1 half. So I'm just going to guesstimate what a slope of negative 1 half looks like. If I go down 1 over 2, something like that. Let's do the next point, go to 2, 2. So I go to the point 2, 2 and plug them both in, I get a negative 1, something like that. Up here at 3, 3, if I plug it in, I also get negative 1. I don't know if that's... And don't worry about your slope being perfect. You just do the best you can to approximate that. I come up to this point at 1, 3. If I plug in 1 for x and 3 for y, I get a negative 1/3. So down 1 over 3, something like that. Negative 1, 1. We get the slope, plug both those in there, we end up with a slope of a positive 1. At negative 3, 3, we get a positive 1 also. At negative 2, 1, if you plug those in there, you end up with a positive 2. So what I want you to do, pause this for just a second, and I want you to work down through, I want you to fill in the rest of those missing holes. So anywhere there's a point that doesn't have the slope, I want you to plug the coordinates in the x into that differential equation to find the slope. When you're done, unpause it, come back, and I'll have all these filled in also. You can compare your answer. So it should end up looking something like that. Okay, once you have your slope filled, what we can do now is we can draw a sketch of the graph of a particular solution. So if you look at example 3, it says start at the point 0, 1. And we want to draw a sketch of the possible solution. When you do that, just be careful. So I'm going to start right here. I'll do a different color. I'm going to start right here. We're not connecting dots. We want to make it a smooth curve, and we want to follow the flow of the slopes. So right here, the slope is 0, and as I go around, right, the slope is curving down. So it ends up looking, and we're not looking, again, we're not going to have the exact graph here. We're just trying to come up with an approximate graph. What does it look like approximately? Now at the endpoints, I don't know what's happening for sure. We're just going to put open points there. We're always going to do an open interval because we don't know what happens at the endpoints. One thing that happens, and the reason why I stopped there, is the solution to the differential equation is a function. If I were to keep going, right there we said the slope is undefined, it's vertical. I'd have to start curving back around like that. Well, that's no longer a function. So a really common error is going too far. So make sure you stop. Yeah, you can go as far as you can while it's still a function. Once it's not a function anymore, you've gone too far. So I'm going to stop at those two endpoints, and we always do the open interval when we set those up. Okay, let's do another one. The next one down below says that we want to do it with the point passing through -1, 1. So let's go to -1, 1. We'll do a different color. So I'm right here. So we're following the flow of those slopes. So right there, it's -1. You know, it's going to be something like this. You're just kind of staying parallel to those slopes and following its flow. That one ends up looking pretty similar to that. I think, is that all it asks us to do? Is it? I was thinking there was one more maybe. Oh, 0, -3, yeah. So let's go down to 0, -3. We'll do one last graph. So if I start at this point, and if I'm following the flow, just kind of staying parallel to them, and I don't know exactly what it looks like, oh, but something like that. Okay, is what it comes up to. So once you have your slope field, if they give you an initial condition, a starting point, you're going to start at that point and then just following the flow of the slopes. Just be really careful not to go too far. And what we mean by going too far is if you go far, it becomes not a function. So if I start curving back around, it's no longer a function, then you know you've gone too far. One thing that can be helpful with that is along this axis, remember we said anytime y is 0 along here, along all those points, that means that my slope is undefined. So that's kind of a natural stopping spot there. If I go past there, I'll start curving back around. Past that vertical, it's going to have a vertical asymptote right there. Okay, so that's kind of how slope fields work and how you graph solutions to differential equations. Again, the note here is don't go too far. You want to find appropriate boundaries. In that case, the x-axis was a boundary because I had a vertical asymptote there, like the slope was undefined. So if I went past there, I'd start to curve back around and it would no longer be a function. So that's the big thing is you've got to make sure that your graph is a function. If you go too far, it's not going to be a function. Okay, this one's, now we're going to actually do this. Back in 7.1, we solved differential equations, so we're actually going to solve this. So let's solve this differential equation. This is the same one we just drew the slope field for. So I'm going to times the dx up to the other side, times the y up with the y. So I have y dy equals a -x dx. Integrate both sides. I'm going to leave that negative on the outside, just factor it out. So I integrate this, I get y squared over 2 equals a -x squared over 2 plus c. And I call it c1. I want to get rid of the 2, so I'm going to times by 2 on both sides. So I end up with y squared equals, right, when I times through there, that 2 will cancel out also. C1 times 2 is just a new c. Take the square root of both sides. So I get y equals plus or minus, oh, I forgot my negative, I'm sorry. So negative x squared plus c, which really means there's two different possible answers. It could be y equals a positive square root of -x squared plus c, or it could be y equals a negative square root of -x squared plus c. So it could be the positive or the negative, it's one or the other. Okay, now it wants me to find a particular solution, and so we're going to start with this. Remember we drew the graph that passed through the point 0, 1. We drew a graph of the solution. So I want to find out, I'm going to find the particular solution for that point. So if I plug that in there, I get 1 is equal to a negative square root of a -0 squared plus c. Well, that would be 1 equals square root of c. I square both sides, so c is equal to 1. So my particular solution is, oh, and side note, I'm sorry. I actually did that incorrectly. I apologize. Hey, we have to choose between these two functions. If my y value is a +1, it has to be the positive square root. So that should be a positive square root there. I apologize. C still does come out to be 1. So my function is y equals the square root of negative x squared plus 1. Okay, what I want you to do, pause the video for just a second. I want you to graph that in your calculator. And what we want to compare it to is, does it look like the graph that we drew up here, the blue one, that passed through the point 0, 1? Does it look like that blue graph right there? So pause the video for a second, graph it on your calculator and compare it to that. What you should have found is that it looks just like it. Okay, it passes through that point 0, 1. So let's go ahead, and now it wants me to find the particular solution for the graph when it passes through the point 0, negative 3. So let's come down here and do the point for the 0. So this time my y value is negative. That means it has to be a negative square root on that one. So we're going to go y equals, so we're going to plug negative 3 in for y, equals a negative square root of negative 0 squared plus c. So that's going to be a negative 3 equals a negative square root of c. I can divide by a negative 1. Square root of c equals 3. Square both sides. So c is equal to 9. So my particular solution is y equals a negative square root of a negative x squared plus 9. Okay, if you were to graph that in your calculator, in fact, go ahead and do that. Pause the video, graph it in your calculator, and we want to compare it to the graph of the green one, the pass through the point is 0, negative 3. So compare it to that graph right there. So go ahead and pause the video, graph it, make sure it matches up with that. Okay, so the connection we want to make here is, what I have a slope field, and I come up with a possible graph of the solution, it's really the same thing. We're doing graphically the same thing we did in 7.1 when we solved differential equations. Whoops, sorry about that. So down here, if I can get that to slide down, we'll go to here. So down here, right, this process of solving it and coming up with the equation is the same process we're doing graphically when we draw the slope field and we sketch a graph that passes through a certain point. So make sure you connect those two in your head. Okay, so we're going to go through and do another one. So what I want you guys to do is, look at this example 5 here. It says for the differential equation y prime equals 1 over y, draw a slope field on the dot coordinate plane. So let me give you a couple points and then you guys can do the rest of it. So if I pick a point, for example, right here, that point's 1, 1, I'd plug it in there. It'd be y prime equals, and really I just plug in the y coordinate, which is 1. So I get a slope of 1. So draw a slope of 1, it'd be something like that. Now something I want you to notice here, if I plug in this point, that point is 2, 1. Because I'm only plugging in the y coordinate, I still just get 1 over 1. So it's actually the exact same. And if I go that, I get the exact same. So what happens, this makes this really fast, is because my differential equation only has a y in it, no matter where I go along there, it's always going to be, that as I go horizontal, move left and right, the slope's going to stay the same, right? If I try this point up here, that point 0, 2, if I plug 2 in for y, I get a slope of a half. It looks like that. Get a slope of a half. It looks like that. Slope of a half, slope of a half, slope of a half. And if I plug in, anyways, you can kind of see the pattern there. So I want you to pause the video, go through and fill out the rest of that slope field, and then we'll come back together and just double check it with each other. All right, so it should end up looking something like that. Okay, part B says graph the particular solution for the points pass through negative 2, negative 1, and 2, 2. So let's do negative 2, negative 1 first. So if I go to negative 2, negative 1, that's that point right there. So I want to graph the solution that passes through there. So I'm going to, if I follow the slope, I'm going to start up here. If I'm following the slope, by the way, if you go along the x-axis, y would be 0. We get undefined slope, which means it has a vertical asymptote. So it's going to be like something like this. And it's starting to get closer to 0. So something kind of like that. Okay, now we're going to the point 2, 2. Let's do that different color. So come up to the point 2, 2, which is right there. Okay, and follow the flow of the slopes. So something, oops, didn't mean to move that around, sorry. It's being funny here, but something kind of like that. Okay, going out that direction. All right, C wants us to solve the differential equation. So we're going to take that equation up there and solve it, and we're just going to compare the graphs to what we got here. So I've got y prime equals 1 over y. So remember, you write it as dy dx equals 1 over y. I get the y with the dy, get the dx with the 1. Integrate both sides. So we end up with y squared over 2 equals x plus c. I'm going to call it c1. Times both sides by 2. So I end up with y squared equals 2x plus 2 times constant. A constant is just a different constant. I'm going to call it c this time. Take the square root. Y equals plus or minus the square root of 2x plus c. Hey, go back and look at that graph, right? That looks like a square root graph. You know, the 2 is doing a horizontal compression, which makes it so it goes up a little bit. It goes up a little bit higher. But that is what the square root function looks like. So that matches pretty well with that. Okay, now it wants me to find a particular solution for -2, -1, and for 2, 2. I'm just going to do one of those. So let's do the point -2, -1, and find the particular solution. Okay, I've got to make sure I choose either y equals a positive square root or y equals a negative square root. This y value is negative, so I'm going to do y equals a negative square root of 2x plus c. Plug in your 2 points, plug in -2 and -1. So I get -1 equals a negative square root of, you got 2 times -2 is -4 plus c. You can divide by a -1. You end up with 1 equals the square root of -4 plus c. Square both sides, so you get 1 equals -4 plus c. Add the 4 over, so c is equal to 5. So my particular solution for this point right here is y equals a negative square root of 2x plus 5. If you take that and graph it, it's going to look, we're hoping anyway, I should have done that in red, I guess, but it should look like this red graph over here, right? That was the one that passed through the point -2, -1 over on that side. Okay, example 6. So these last 2 examples, on the AP test, they like putting, usually it could be a free response question, but it's more commonly not a free response, it's more commonly a multiple choice question. So the 6 and 7 are the 2 different types of questions they ask you. So let's do number 6 first. It says, which of the differential equations below matches a slope field shown at the right? So if you're doing this problem, right, you're trying to find a differential equation that matches it, I would just pick points on my graph and I'd plug the x and y into my differential equation to see if it gives me the correct slope. So what I mean by that is just pick a point on the graph. It doesn't matter where. So I could pick this point, for example. That point is 1, 1. I want to plug that into each of my differential equations to see what I get. So if I plug the point into here, I just get y prime equals 1. Could that be a slope of 1? Maybe. That looks more to me like it's maybe like 2, but possibly. If I plug my point into this one, I get a slope of 1. If I plug my point into this one, I get a slope of 0. There is definitely not a slope of 0. Like that is not a slope of 0. So we can cross off C. If I plug 1, 1 into here, 1 plus 1 squared would be 2, so I get a slope of 2. That looks like a slope of 2. If I put my x into there, I also get a slope of 2. So if I'm looking at this does not look like a slope of 1, so I would cross off this one and this one. It could be D or E. So let's pick another point and try it again. And it doesn't matter which point you choose. So we could use this point right here. That point is 2, 1. So plug in your x and your y. So on this one, if I plug in my y, I'd get 1 plus 1. It should still have a slope of 2. If I plug in my x, I get 2 squared is 4, plus 1 is 5. I get a slope of 5. Well, if you look at the slope at 2, 1, these 2 slopes are the same. It look like they're both about 2. So my answer is D. Okay, that's the one. So all you're doing is picking points in your slope field. You're plugging in the coordinates, and you're seeing if you get the slope that's on your slope field. And if you did, you're just going to narrow it down. Sometimes you'll try a point, and it'll only knock off 1. But you just keep going until you have it narrowed down to the correct differential equation. Okay, I want you to compare 6 to 7, because this is a little bit tricky. 7 looks really similar to that question up above. You still have a slope field. Now the difference is, it's asking which one of these could be a solution to that slope field. So this is not giving us the differential equations. If you look at the choices up above, they were y prime equals, y prime equals. It was talking about the slope or the differential equation. These are talking about the solution. So what you're trying to do is saying which one of these graphs could match with that slope field. So think about what the graph looks like. We know that y equals e to the x looks like this. All right, that's y equals e to the x. That does not follow the flow of those slopes. So it is definitely not A. We can cross it off. Y equals e to the negative x. So that is reflected across the x-axis. So it's something like this. You know, it's coming down like this. That looks like it could be it. I mean, that matches the flow of those slopes pretty good. But just compare it to the others. Let's go through the rest of them. Y equals negative e to the x comes along this way, right? It's reflected down and comes up that. That doesn't follow that at all. Like I've got these slopes are negative. My slope is positive. So it's definitely not that one. Let's do E first. The ln of x, if you remember, has a vertical asymptote. So we can almost already eliminate that because that means there should be a vertical slope along there, but it would come up like this. Right? That does not follow the flow of those slopes. So we can cross off E. So the last one is y equals negative ln of x. Negative ln of x has a vertical asymptote. It comes along that, and then it's curving down that way. That's a little bit closer, but the problem is if it came up there, you would need a vertical asymptote, and these slopes along there are not vertical. So I think we can cross that one off. So our final answer comes out to be that. So on number 6, you're picking points off your slope field, plug the coordinates into your differential equation to see if you get that slope. On 7, you don't have the differential equation. Instead, you're just saying that you have the solution. So you're saying which one of those graphs fit the flow of the slope, that fit that slope field as you go down across there. So those can be a little tricky. It's easy to mix those two up. But those two questions are the type of questions that you usually run into when you take on the AP test. All right, that's all I have for this section. Make sure you get questions to me. Good luck.